Let's begin. So a couple of you saw Tom playing around with this in school, right? You notice what happens here? Turn the hair dryer on, put the ball there, then you go left, then you go right, forward, back. It doesn't change now. If I change the angle for trouble, when I get to a certain point, it's going to fall. And the reason it's falling is because gravity is flowing down there. When I tilt the angle, gravity overcomes it. But the question in your text was not about why it doesn't fall, but about why it remains stable. Right, that's the key here. It doesn't fall, and that's obvious why. Air pushes up, gravity pulls down, you're in a state of equilibrium, the object balances. I asked you guys about skydiving, remember? And I think you were actually the one that answered, Tom, said you've done it before. There was like skydiving zones where it's just a big fan at the bottom and it propels you upward. That's literally this right here. But the question is not why is it not falling? That's the easy answer. Air pushes up. But the question is really, why isn't it moving left to right and leaving this little area above the hair dryer? And you see it's like slightly rotating. You see it slowly rotating. So why is that happening? So what's happening based on your studies? Yeah, first guy.
So the high velocity of the air is like a stream.
Go ahead. I'm going to draw as you talk.
Creates like a low pressure, I guess, inside of the stream, and then there's a low velocity outside of the stream.
Low velocity or just?
Or it's just no velocity of the air outside. So like to compensate with the high, like using this principle, like there has to be a high pressure going. There's a high pressure outside of that stream, keeping the ball in like a kind of one area.
Yeah, and that area is like a cylindrical shape like that, right? So if I think about the hair dryer is a great example because it's circular. Now, it doesn't have to be circular, but it does help to be circular. When the hair dryer head is circular, it creates this channel or this column or cylinder above it. Think about air coming out of here. It would be a cylinder. There's a cylinder of air above here that is very high velocity and therefore low pressure. If there's low pressure in this cylinder I've drawn here, and outside of it is all higher pressure, and it doesn't need to be high pressure, but higher, relatively speaking, higher than what's in the cylinder. If there's higher pressure out here and lower pressure on the inside, whenever there's higher pressure and lower pressure, we get a net force acting. And this net force is acting inward on the cylinder. We're trying to draw those four arrows acting inward. So due to the higher pressure around it, every time the ball does this, ready? Every time the ball starts to move right or left, it gets bounced back in. It gets bounced back in. But it's happening and it's keeping it level for you. But if you think about this, it's kind of like if you were to think about a balloon with gas particles bouncing around inside the balloon. There's some sort of a barrier or a boundary that's keeping them within that spherical shape or whatever the shape is. Same concept here. Okay, there's this channel that's staying inside of here because the higher pressure on the outside. Very easy one, but a nice one to see, right? Nice one to see. And how is it staying vertically stable again? What's balancing its weight?
Because isn't it the higher pushing up and it's like the mass is equal to the force of pushing?
Close, but you're misstating your words. But I know what you mean, but you're not saying the words right.
The weight is equal to the amount of air going up.
Not the amount of
I
air.
mean, the force of the air.
Good. The force of the air. So Daniel, it didn't have to be hot. It doesn't have to be hot air. Let me hold it. So the force of the air pushing up is balancing the weight pulling down. Those two things are happening to keep it in vertical equilibrium. The horizontal stability comes from the higher pressure outside of that channel. Okay, very similar. Very similar to Bernoulli's principle for an airplane, where the higher pressure on the bottom of the wing causes a lift force upward. This is causing a force, though, inward on this case. Inward. Okay. What questions might you have from the problem set that haven't been addressed maybe in office hours? A lot of you that I see right now were in office hours, which is great. But what other questions might you have, or those that weren't there want to ask something? Or that were there, it doesn't matter. Daniel, go ahead.
Can you just go over the submarine one again and how you get the highest possible, or the highest possible?
The master. Oh, not the master one.
The submarine one?
No, I think I'm thinking of the mattress one where you have to find the highest
Mass you can add before it'll sink.
Yeah, that was
Okay, sure. So let's go over real quick. This was problem number
81.
Thank you. 81 in chapter 12, right? Chapter 12. So here's your mattress. 12.2? Thank you. So here's your mattress right here. Okay, very rough drawing of it. And what we notice is that this mattress, upon its own weight, easily rests on the surface of the water. Easily. It's an air mattress. You've blown up an air mattress before, they're very buoyant. They have a lot of air inside them. They have very low density. We're told that the dimensions of this air mattress are 2.3, 0.66. I thought I had it right. Now, before I put those units, this is what it was given as. So the first step is to write this as 0.14 meters. Okay, that's the first thing you want to recognize. So given in centimeters, make sure to convert that to meters. You're also told that the mass of the mattress is 0.22. Is that right? Okay. Trying to write this morning. So that's the mass of the mattress itself. So tell me, before I go into the problem, what's the density of this mattress? Or how would I figure out the density of this mattress?
You multiply the length of the front side, then M over V.
Very good, Dan. M over V with LWH, as Dan just said. So there's the density of this mattress. Again, the volume is LWH, it's prism. You should know the volume of the prism. It's something I'm not going to give you. LWH is the volume of the prism. And I'm not going to give you shapes that are going to be weird or morphic, like, a parallelogram prism or like a trapezoidal prism. It's not going to be something funky. It'll be a rectangular prism or cylinder, something that you would know. We all know cylinder volume? Mm-hmm. Very easy way to get it. You take a circle. Circle is pi r squared. And then you times by the height. Remember, whenever you have a prism, you can take the area of the base and multiply it by the height. And the base is a circle in that case. Pi r squared times h. And just like this, LW, which is the base, right? Times h. Now, the density of this, what do we get as a number? Can somebody calculate this real quick? And it doesn't matter for the problem, but I want to know. I'm just curious. Luce, what do you got for this?
Oh, wait, I don't know.
Oh. Just this part I meant, not the answer. I don't want the answer yet. What do we get for this? Somebody check it real quick, please. Yeah, Gigi. 0.212. 212?
0.212, yeah.
Thank you.
Oh, it's 0.213. No.
Works. Is that close even? It's close, right? Okay, we're good. Now, the only reason I want you to calculate this is to recognize what will happen if this object is placed in salt water, fresh water, pretty much any liquid, not fluid, because fluids can be gases also. If you put this in any liquid, what's it going to pretty much do? It's going to float. Why do you know that right away? How do I know that this object is most likely going to float out? Good. And how do you say really low? How do you know this is a really low value? How do I know what 0.212 is? What are you comparing it to, Alice?
Or just water.
Yeah, what's fresh water's density? What is fresh water's density? 1,000 kilograms per cubic meter.
Oh, no.
1,000.
I
Straight.
gave the wrong number, sorry, I forgot to divide by 0.22.
Okay, so what does that come out to be?
1.04.
1.04? Okay, still a very small number. That's fine.
Yeah, because she just at the bottom, so that you divided it.
Is that correct? 1.04?
Yeah.
Okay. Either way, right? 1/1000th of the density of fresh water. So most liquids are going to be a density of water or maybe a little bit lower, like oil. Oil sits above water when it separates. Oil doesn't mix well with water. We know that, mixing with oil and water. But it has less density also, so it separates. So oil is a little bit less dense. But it's not a density of 1 when water is 1,000. Remember, the density of water that is 1 is in grams per cubic centimeter. That was from chemistry class last year. If we're in kilograms per cubic meter, it's 1,000 for fresh water. So as Alex said, yes, this will most likely float, and it will float on water. What will cause it to sink in water? What causes any object to sink in the fluid that it's resting on currently? George? Okay, weight or mass being added to it eventually would cause it to sink. I want a more specific answer than just that. You're right. Adding mass or weight helps, but more specific.
When the density
density exceeds that of the fluid, then.
Good. We had two conditions. We said this was one condition would cause it to sink. The second condition, which some of you looked at for this problem, which is fine, you can do it, it's a little more work, but you can do it, is when the weight is more than buoyancy. Either of those conditions cause sinking. And they're pretty analogous, actually. If the weight is more than the actual buoyant force, then the object's density will be more than the fluid's density. If this is true, this is true. If this is true, this is true. Okay? But either way, we could use to verify this answer. Because the problem gave me dimensions and it gave me mass, I'm probably going to want to just focus on density because it's easier. So currently, look at the density. It's only 1.04. It's clearly not more than 1,000. What are we doing with this problem? We're taking mass and we're dropping it on top. Here's the thing about this problem that I don't love, but I still do assign it because I want you to get the idea. If I add mass, I'm going to put like blue dots as in mass, like coins or something, I don't know, metal. Okay, I'm adding mass to the top of this mattress right now. If I added mass to the mattress, what am I also adding technically? Volume. But do you give anything about volume of the mass that you're adding? So here's the thing. To solve a problem like this, the assumption has to be made that when you place those masses on top of the mattress, the overall volume doesn't change. Assume that the mattress kind of sinks in a little bit, and the sinking in gets taken the place of by those masses. So we have to make the assumption, it's a wild assumption, that this is still the volume. Even though when I add an object on top of the mattress, like if I were to lay down on top of a mattress, the volume of the mattress and me combined is bigger than just the mattress, clearly. So the assumption we have to make here is that we're putting a really thin piece of mass that's not adding volume to this. Do you follow me right here? Because we're giving nothing about the volume. Now, with that said, here's how the formula changes. We've got the same thing as this right here to find density, but now we're adding the mass of those extra objects. Again, the mass of the mattress plus the objects divided by volume will give us the overall density of the combination mattress mass together. So this number is no longer valid. We don't know the density, but we know that this number goes in for the object. So we can write this as and you could put equal to instead of greater than. I like to think of threshold limits as greater than. Any value of mass greater than whatever we get will cause it to sink. So again, when this number is more than 1,000, it sinks. So let's take this decimal, 2.3 times 0.66 times 0.14. Let's get a number for that. Multiply it up, and then subtract the 0.22. Okay? And you'll get a mass value there. What does that come out to be for a mass?
212.34.
I just did it differently. Like, I found the volume, and then I did the density formula, but like, found the mass, and then subtracted the mass they gave.
You get the same answer? I know what you did. I know what you mean. It's totally fine. I like to try it as one thing. You can do it separate parts. That's fine. Yeah.
I'm kind of confused on how you got 284.3. So when you multiply,
So we're going to take the result of these three, right? Multiply it by 1,000. What do you get from that?
is it 0.66? That's how I know it.
0.66, 2.3, 0.4.
And then you subtract 0.22, I think.
And then subtract the 0.22 to get the m by itself. Okay? So again, the assumption is that we're not adding volume. We're not adding volume. If we were adding volume, the problem would get a little bit trickier, because what would happen? We have to say plus V But then how many variables would we have? Can we solve that? So it wouldn't work too well, would it?
Would you give us something?
I could, theoretically I could say, for every 1 unit of mass, you can get 2 units of volume. So you can put M and put 2M down here technically, but I wouldn't be doing something like that. That's just it's kind of like a mean problem in a sense. All right, what else? What else from the problem set? Or from 12E. A lot of you I know started 12E. You spoke about it this morning too. There's a whole set of questions under documents and handouts called 12E. I also put a video up for that I had a period to go over last year in one of the sections that I kind of went over about 6 of those problems and I talked about them. So if you prefer listening to explanations versus reading them, the solutions are listed under documents and handouts, but I also put up a video under videos from class that has 12E. I don't know how many of them I actually covered, to be honest, but I did it one of the years. I think it was like 4 years ago I did that video, actually. Anyway, so any questions? What other questions on problem set? On 12E? On magnetism? We haven't talked about magnetism. What can we review about magnetism? There was a lot. I can go over every single bit because it's not involved. Right-hand rule, sure, let's start with that. All right. Let's say we've got a wire, and that wire is connected to a battery. Okay, one end of it is connected right now, so I call this a what circuit? Right now it's a what circuit? Open circuit, very good. If I do this, closed circuit. You'll notice that the wire has insulation around it. All wires can have insulation around them. The wire is then wrapped around what it looks like an iron nail or a nail that contains some ferromagnetic material. So if I were to connect the wire to both ends of the battery, it would produce current. Current would travel through the wire. Now, when current travels through a wire, we came up with this idea or this kind of phenomenon that it produces magnetism. So let's draw a quick profile. Let's say that the current, which it always does, leaves the positive terminal. When the current goes around the wire or goes through the wire, we get this looping effect of magnetism. So if I take my thumb, take your thumb please, put it in the direction of current, it means that the magnetic field would wrap around this wire like this. Take your fingers and curl your fingers. The direction that your fingers curl like this is the direction of the magnetic field. So above the wire right here, the field is into the page. Below the wire, the field is out of the page. Now, it's two different answers. Think about it. When your fingers are above the wire, the field goes into the page.
And if you go like that,
And if you continue curling, below the wire, it comes out of the page. Now, if the wire is itself coming out of the page, the field goes counterclockwise. If the wire is going into the page, again, Daniel, out of the page is the current. The field is your fingers curl, which is counterclockwise. Into the page means it goes clockwise.
wait, but what if it's going on and you hold it like that, and then that's clockwise?
No, this is counterclockwise.
No, if you do it like that. Like,
That's with your left hand. You
Oh,
do the right hand with your left hand.
Are you a lefty? Are you a lefty?
okay, never mind.
Sorry, that's fine. Right hand rule, yeah. Zoe.
There was one question
Yeah.
where it was like, towards you.
Out of the page. So towards you, away from you. So towards you, magnetic field curls counterclockwise. If the current is coming towards you. Current is coming towards you. Thumb is current, fingers are field. So in this problem, here's how we would denote this. God bless you. Watch the way I'm going to draw this, please. Okay, again, thumb in the direction of the current, fingers into the page on top. So I'm going to go like this. Ready? So this is the magnetic field as it goes around here. So if you actually, a good lab that we didn't have time for, I've done it a couple times. We didn't have time this year. But when you do the circuits, I've done this extra piece where I bring out compasses. And what you actually notice to prove this law is that the compass direction changes next to the wire. And it pretty much shows you there's a magnetic field around it. And I showed you an image of that, if you remember. The wire was coming out of a piece of wood and the compasses were all lined up in a circle around it. But if you actually take a compass and put it next to a wire that's carrying a current, you'll see the needle deflect because of the magnetic field around it that's produced. But that's what you're seeing, that's what's physically happening. Now, remember that the magnetic field around the wire is a function of several things. What did we say it was a function of? What's the magnetic field strength a function of? Length of the wire. What else? The thickness will affect it for sure because it carries more material. If it's a thicker wire, it carries more current. So we got the length of the wire and the current. Temperature always affects all things, but not as dramatic here. But yes, it definitely affects all things. Something else. The material itself. So we've got, again, the length of the wire affects it, the material itself, the current traveling through the wire. One more thing. What'd you say? Frequency of what?
The current.
It's a general word, you know?
The shape.
Not the shape. The number of what?
Loops.
Coils. Loops. Okay? So, the more concentrated the coils are, the stronger the field is. Every loop of a coil is creating another field, really. So if you guys remember when you did the DC motor lab, you had to coil that wire together over and over. The more coils in there, the stronger the actual thing was. The faster it spun, you notice. Okay? That's what we're seeing here. Now, this is not perfect because I'd have to tape it and stuff, but really, do we have a paper clip anywhere? This would actually pick up the thing as electromagnet, right? So this produces a magnetic field around it. I don't know if it's going to work. The paper clip has insulation on it.
Is there a problem?
All right,
Can we go over permanent magnets?
Sure. All right, so let's talk about a permanent magnet. So first, how to create permanent magnets, right? How to create them. One way is what we talked about as induction. Remember induction? So it's inducing a magnetic field on a ferrous material, on a ferromagnetic substance. And the way that works, if you recall, I drew an image of it. You take a very strong magnet, such as this, and between that magnet or in the magnetic field, you place a ferromagnetic material and you leave it in there for a certain time. Over time, what happens to the magnetic domains in that red material is that they all align themselves and they themselves become polarized, is the right word for this, really. They create poles. And this material becomes in itself a permanent magnet. So that's one way, which is just using magnetic induction. Another way is just simply permanent magnets that exist in the earth. So certain materials have natural polarity to them. So something like, looking at iron ore and like excavating it from the earth's surface, that will have magnetism to it naturally. Whereas this has iron in it, but it's not a magnet itself. The magnet around it is what's causing it to become a magnet. Now remember I talked about two types of permanent magnets. One is called the soft magnet, one is called the hard magnet. And the soft magnets are very easy to make magnetic, or soft materials, I should say, magnetic terms, can easily be made a magnet. but they can easily lose their charge or lose their polarity, I should say. Whereas a stronger one would take a lot to make it a magnet, but it would retain that magnetism. It would retain it for a longer time period. Over time, all magnetic things start to lose their magnetism. I've had magnets in the cabinet for years that just don't work. I think I mentioned it to you guys. I was going to try to make them back in magnets, but I didn't throw it
The
in.
magnets for the were so strong.
Yeah, those were strong magnets. And some of these ones here. Actually, I should probably just show you this one. Here, let me do this one because I haven't done this yet with you guys. So,
Yeah.
Yeah.
No, I was just saying.
give me 1 sec. I'll get this out to you guys.
Wait, what?
Keep speaking my magnets. We've got magnets lined up. These are both magnetic. It's not nothing's going to fall off the track. Okay, magnets here, here, and here, and then just ball bearings. Now, if you've ever seen Newton's cradle, the momentum from one ball bearing transfers to the other. This is using conservation of momentum, really, and magnetism. Unfortunately, these ball bearings are a little bit rusted, so they're not perfectly, lack of friction. So there's some friction here. What I'm going to do, though, is talk about this. So I'm going to apply a certain amount of force to this to cause it to adhere. And we're going to see like chain reaction of magnetism occur. And the magnetism amplifies each time. Because the first ball hits this, gives velocity to this one, but it gets pulled by the magnet here, which increases the velocity, which gets pulled by this magnet, so the velocity increases over and over. So for those that ever talk about like a railgun in a video game, this is what a railgun really looks like. So, Dennis, I don't know how far this is going to go. I know it's going to go far, but you guys over there, just keep
Catch it, Bruce.
You ready? Keep your hands up. Maybe close your iPad. I don't think this goes very far. It might only go like a foot. We're going to be like that now. Ready? So I used to have 3 more in each type. Let's try one more time. I can do a little bit faster. So, the more ball bearings you have, the faster they're going. And I had 3 more of these and they're gone. I don't know where they went. Is that one of these? Is there any more? Yeah, more still.
Wait, you got 3?
I'll try it again. Ready? Put in more. One more of each would shoot him first. So again, the velocity is increasing because the first marble has velocity. It hits here, transfers the velocity into the last marble. That marble then has its own velocity, which gets sped up when it gets closer to the magnet. It transfers that velocity to the next one, which gets sped up as it gets to the next magnet, because the magnet is pulling it toward it. So each time the velocity is getting a little bit bigger. So if you have this kind of an arrangement infinitely many times, it would just keep getting faster and faster and faster and faster. That's how, if you think about like the Hadron Collider and those particle accelerators, that's how they're working. They're using electromagnetism to constantly accelerate the velocity of the particles. The goal is to get them as close to the speed of light, the less the speed of light as possible.
Don't those things like stretch like so?
Was they what?
The particle accelerators are like huge, like
Yeah,
they like
they're enormous. They go underground. Yep, for miles. Where'd that one go over here? You got it?
Thanks, Dad. Like what is it? They just want to like come like smash two particles.
Yeah, those are particle accelerators and colliders. They want to collide them so they can see what they get. But those are, the one you're thinking of is, that's underground is in Europe. It runs like miles underground.
Right? Yeah. That's the one in Europe.
It's pretty intense. Yep.
It's like a vacuum, right? Does that have to be a vacuum, right?
Say again?
Is it a vacuum? Like when they go.
Yeah, absolutely. Or else, is this mine or is this yours? Yours? Alright, so let's talk about this. In the other class I spoke about this for a second. A question was asked about this. So, with fluids we've used this equation a couple times already. And recall this equation is a continuity equation. It tells us that the cross-sectional area varies, and if that happens, the velocity itself varies. Now, on the test, I can give you the cross-sectional area, and you can figure out velocity. I can give you velocities, you can find area. But when I give you something like radius, you notice you have to use a circle. Pi r squared goes in for a. So this is what we're talking about for a pipe that has a circular cross-section. But not all pipes have circular cross-sections. A lot of ductwork in ceilings and in buildings is actually rectangular, not circular. So if I were to tell you that it's a pipe that's a rectangular pipe, what would the area function be for that? LW instead of pi r squared. Is that clear what I'm saying? So it depends on what I give you as a shape, that area changes for the function you're using. But it's not any more difficult. I just want to make sure we're aware, because the question was asked in the last class, and it seemed to be confusing, but it's just area, whatever shape it is. All right, that was the relationship that we noticed. They're indirectly related. Indirect. And the same thing with Bernoulli. If we have higher velocity, we have lower pressure. So velocity is indirectly related to area when it comes to closed systems that are pipes, and it's indirectly related to pressure. And that's not always a closed system, as we've seen with the hair dryer, with the shower curtain that gets pulled towards your body, with lift force on a wing. Those are open systems, they're not closed systems. Yeah?
Is that V volume or velocity?
Velocity. Which one? On the right?
V with the little thing going.
That's volume. Remember, this is a volumetric flow rate. Volume over time. Mass over time, mass flow rate. Velocity, distance over time, is a displacement rate, aka velocity. Other facts. How does the pressure in this container, please, how does the pressure in container A differ from the pressure in container B? I want the pressure at the bottom of the fluid. At the bottom of the fluid, I want the pressure. How does the first and the second container differ from one another? How do they physically differ from each other? Lucy, what are you thinking?
One has like the atmospheric pressure or density or P, whatever, and the other one doesn't.
Correct. So if you calculate the pressure, here you need the atmospheric. But here the pressure would just be rho GH. Why is that? Why is that, Alex?
Oh, I also have a question, but I think you might be able to explain it.
Okay.
Is it because the
Ask a question.
is there atmospheric pressure on the other one because it's pushing down the container, and is that creating the air? Or no?
No, so that's the thing. So when the air pushes down on the container, The container's own structural integrity is pushing back. It's not the fluid on the inside there. Now, there is
So
fluid
it's not
pressure
like pushing air, which is causing pressure.
Yeah, so it needs to be open system. And when it's open to the environment, you'll have the atmospheric pressure affecting it. So you'll hear me say open to the atmosphere or closed to the atmosphere. If I say that it's a closed system, or if I show you a diagram that's physically closed, you need to know to use the one on the right. Like a tire, when you're pumping, is not total pressure, it is gauge pressure. The tire is closed. The atmosphere is not affecting the tire at all.
So is the second PGH, the P is that density? Or
Those are both density. It's the density of the fluid, rho F.
Oh, okay.
Okay? And H is the depth of the fluid. The depth of the fluid.
And then the one on the other side is the pressure. The other side is the pressure.
Correct. And this is your atmospheric pressure.
Also, in one of the questions it said that the atmospheric pressure was like 0, 1, 3. So should we use 1 times 10 to the 5th, or should we use that?
So 101.3 kilopascals is where you're thinking of. 101.3 kPa is the same as 1 times 10 to the 5th PA.
Okay.
Because 101.3, you have to move the decimal 3 spots, which makes it 1 times 10 to the 5th.
Do you want to answer just Pascals?
Pascals.
Okay, and what's, is just 10 to the third is the difference? And then is it
Yeah, because kilo is 10 to the 3rd.
Wait, so for KPA, you just move it 5, or like it's 10 to 3?
So what she asked is these two numbers. A lot of textbooks use this value, and then some others use this value. They're really the same thing, because this becomes 101,300, and this becomes 1, 2, 3, 4, 5. So take a look at the numbers. You see how they're pretty much the same thing there? So yeah, 1 times 10 to the 5th, or 101.3 kPa. Either is fine. On your formula sheet, I write this, so you should use what I have on the formula sheet.
Yeah.
But the textbook does reference that number at times. Yep. George,
What do we do in class yesterday?
what did we do in class yesterday?
Oh, 10.
We did 12, 3, and then we did the
We did 2 examples. One from 12.2 that we skipped on an object being submerged and then being inflated. The one that I had you guys watch for homework. And then we looked at a little more of 12.3. That was probably it, actually. What did we do at the end?
I thought we did some
Oh, I gave you guys free time to work on the rest of the lab if you wanted to, but it was only like 5-10 minutes. It wasn't much time. So it was really finishing up lessons 12.2 and 12.3, and we just had a discussion about them. Okay? Yeah, I would look at that stuff. Look at the videos or go through the notes at least.
Wait, so just that, the thing on top is just to convert from kilopascals to...
Yeah, kilo is 10 to the 3rd, right?
Yeah.
So I took the decimal here, move it 1, 2, 3 spots. Then a kilometer to meter. What else? What other questions might you have?
I know I said no, sorry, but I'm just making sure the only units that we have to do are...
Please listen.
So we have to make sure everything's in pascals, not kilopascals.
Yeah, I would have everything in pascals.
Okay, and then...
And what is a pascal really?
And meter?
A Newton per meter squared. How do I know that? My formula for pressure is force over area. Remember the basic pressure formula with hydraulic lift? Force over area. Hey, what's mechanical advantage? I'd love to come up.
Efficiency?
Okay, I like that. A little more than that.
Is it input over output? Right here, output.
Output over input. But what is it? Yeah, it's output over input calculation-wise. What is it? What's mechanical advantage?
It's a force that you multiply the factor by.
Like when
A
you
factor. You multiply the force.
So wait, so when do we
Yeah.
use it?
It's
When do
like-
we use it?
So when do we use it, right? If I put in 15 pounds, but somehow I get out 60 pounds,
Yeah.
it's a factor of 4. 60 over 15. So it's the increase that I get from what I'm doing. Now remember, there's always a
Loss of...
something, right? There's something that is a cost. What was the cost? Who remembers? I talked about this. Like a jack in a car. How much do you have to do this to jack the car?
60 times.
Like 50, 60 times, a lot, right? So you might be pushing for how many? 60, 50 feet. How far does the car lift? So remember, you're putting in less force, but over a longer distance. What is work equal to? F times D, right? So are you doing the same work? Think about it for a second. Think about the work you put
You're
in.
able to lift the car. Right?
To lift a car, ready? To lift a car, you need to do a certain amount of effort or energy to lift it. And if I think of it as work, this was work from earlier in the year. Okay, this was work that we used. If I put in very little force and I want to get the same energy to lift the car, I need to put it in for a longer distance. So the same thing with the hydraulic press. So Steve's
So
an
it's just
example.
like a hydraulic press.
Like a lever arm, yeah, cheater arm.
With the, it's just like if you're just like lifting the car because it's just a lot of force but not much distance. And then if it's a hydraulic press, a ton of distance, or like with the car jack, it's like a ton of distance, but you're not putting all the force.
Precisely. So this, remember the syringe here? I push this down probably about 6 inches or 6, 7, about 6 inches down foot. I push this down all the way. The bladder only increases slightly. You can barely see it, almost not see it at all. If you look at this carefully, even better view, you can see it. You see the bladder kind of expands a little bit. Again, you're getting very little distance increase on the other side.